Hello friends, in this video we are going to study the block diagram of 8251 Programmable Communication Interface, which is also known as Universal Synchronous Asynchronous Receiver Transmitter or USART. So let us start with our topic. The 8251, it is known as the Programmable Communication Interface because it is acting as an interface between the microprocessors and the peripheral devices. When the microprocessor it is communicating with the peripheral devices, it has to convert the data because it is dealing with the parallel form of data. So it has to convert that parallel data into serial data for the transmission. Now this serial data, it is received by the peripheral devices. Peripheral devices also deals with the parallel data. So there the serial data is converted into parallel data. Now when the peripheral devices, they are transmitting the data, they have to convert it again into the serial form. Again, the serial data, it is received by the microprocessor, and microprocessor has to convert the serial data into the parallel data. So if we represent it diagrammatically, if it is our microprocessors, there are various families of microprocessor like 8085, 8086, 8088. Okay. So microprocessors, when they are communicating with the peripheral devices, or any type of devices they are communicating with them, so they have to transfer the data and also they have to receive the data from the peripheral devices. Now microprocessor, it is dealing with the parallel form of data. Parallel data means that all the 8 bits of data, they are available to the microprocessor. Now this parallel data, when we are transmitting the data to a peripheral device which is located at a very far distance from the microprocessor, so this parallel data is converted into serial form. Means 1 bit by bit the data will be transmitted, 8 bits will be transmitted 1 bit by 1. Now this serial data, when it is received by peripheral devices, they again converted into the parallel form so that they can process that data. Now when these peripheral devices are sending the data to microprocessor, they have to convert the parallel data into again serial form, and microprocessor converts the serial into the parallel so that it can process that data. Now in this conversion, the microprocessor gets busy in this work and it cannot perform the other operations. Okay, it will be engaged in the conversion of parallel to serial and serial to parallel form of data. So instead of doing that work itself, microprocessor uses an interfacing device which is the 8251, known as the Programmable Communication Interface, and sometimes it is also known as USART. Okay, so this is used by the microprocessor for this parallel to serial and serial to parallel conversion. So microprocessor, it is free from that task, and this conversion task will be performed now by the 8251. So the processing of the data will be fast by the microprocessor. Okay, so this programmable communication interface 8251, also known as USART, what it does, it accepts the data characters from the CPU or the microprocessors. It is going to convert that into serial form and then provide it to the peripheral devices. Again, it is going to accept the data from the peripheral devices in the parallel form, going to convert it into serial form, and again it is going to provide it the parallel data to the microprocessor. Okay, so what all the conversion process, it will be now done by the 8251. So 8251, that is why it is known as universal synchronous asynchronous receiver transmitter. Synchronous and asynchronous, they are the two modes of transmission. Okay, so it can work in both these modes. So it is known as synchronous asynchronous. It is working as the receiver also and as a transmitter also. So that's why it is known as the universal synchronous asynchronous receiver transmitter, accepted universally by all the manufacturers as an interfacing standard that can be used whenever the microprocessors family like 8085, 8086, 8088, they are communicating with the peripheral devices. So its short form will be USART. So it is also known as the USART. Now here we will study the block diagram of this 8251 programmable communication interface. The block diagram, it includes all the functional elements of the 8251. It will indicate us that what are the functions performed by the various elements in this chip. So we can say that the block diagram shows all elements. It is going to show us all the elements of the programmable chip. It is the definition of the block diagram, that what is the block diagram of a chip. Block diagram shows us all the elements of a programmable chip. It includes the control register and the status register. So in the block diagram of 8251, we are going to see all the elements of 8251 along with the interfacing signals, control register and the status register. Now the block diagram of 8251, it is broadly divided into 5 sections. First section is the data bus buffer. Second section is read and write control logic. So these are the 5 sections in which the block diagram of 8251 it is divided. In the first data bus buffer, we are going to see how the data bus is interfaced with the 8251. Read write control logic will include the control register and the status register. Modem control include the interfacing signals which are used when modem is interfaced with 8251. Transmitter section will include the transmitter part of the USART, and receiver section will include the receiver part or receiver circuit of the 8251. So let's start with the block diagram. This is the block diagram of the 8251. You can see in this block diagram we are having 5 sections. First is the data bus buffer. Second section is here, the read and write control logic. Third section is here, the modem control. Fourth section includes these two blocks, transmit buffer and transmit control, that is the transmitter section. And fifth section is the receiver section. It also includes two blocks, receiver buffer and receive control. You can see that in this block diagram, not only the various elements but also the interfacing signals are also shown here. The interfacing signals are like the reset, clock, control and data. read, write, chip select, DSR, DTR, CTS, RTS. Here also RX ready, RXE, sync detect and break, RXD, TXE. These are the interfacing signals. So we are going to we will study each block one by one along with these interfacing signals. So let us first start with the first section, data bus buffer. So data bus buffer, it is a three-state bidirectional buffer, means tri-state bidirectional buffer is there, which is used to interface the 8251 to the system data bus. Okay, you can see that here we are having the in the block diagram the data bus buffer, it is connected to the internal bus line of 8251. Also it is connected with the data lines of the microprocessors. In the microprocessors we are having 8-bit data lines, so from D0 to D7 we are having 8 data lines which are connected with the data bus buffer. So whatever data the microprocessor want to send to the 8251, that data will be first stored in the data bus buffer and then that data will be transmitted to the transmitter section. Now whatever data the microprocessor want to read from the 8251, that data will be provided by the receiver section to the data bus buffer and then microprocessor will read that data. Not only data but also the control words. If the microprocessor want to send the control words or write the commands into the control register, that is also provided through the data bus buffer. Also the status information of all the signals and the 8251, that status information is also provided through this data bus buffer. So we can say that whatever data, whether it is transmitted or received by this 8251, that will be stored in that data bus buffer. Whatever communication the microprocessor is doing with the 8251, that communication or transfer of data takes place through this data bus buffer. So here we can say that the function of this data bus buffer is that data is transmitted and received by this buffer. Now, when the buffer is going to transmit or receive the data, that command will be given by the microprocessor. When the microprocessor gives the control signals to the 8251, so according to those control signals, data will be transmitted or received by the buffer. So, the data is transmitted, received by buffer upon the execution of the instructions which are given by the CPU. Now here the data, it can be the command words also and status information also. Okay, so the data, command words and status information, all these three, they are transferred through this data bus buffer. Now this data bus buffer, because it is a tri-state bidirectional buffer, so it is working in both the direction. It is sending the data also and it is receiving the data also. And that data, it will be an 8-bit data. So we can say that the data bus buffer, it is an 8-bit register which is providing us the double buffering. In this data bus buffer, we will have 8-bit register which is providing us the double buffering, means in both the directions it is working. it is receiving also, and it is sending also. Now the next block or in the block diagram or next section we can say is the read and write control logic. The function of this read and write control logic is to generate the control signals like read, write signals. They will be given to the 8251 by the microprocessor through this block. So according to these control signals, the operations are defined by the 8251. If read control signal is given, means it has to read the data. Write is given, means the data is written in the 8251. Then CS is activated, means 8251 is selected by the microprocessor. Reset means that the 8251 it is going to reset all the values, all the commands and modes. Then C and D means command is selected and data is selected. So whatever function the 8251 is doing, that function is defined by the read and write control logic. So let us study this block. So what this read write control logic is doing, it is interfacing the 8251 with the microprocessor, and it determines the functions of the 8251 according to the commands given by the microprocessor. So this read and write control logic, it is interfacing the 8251 with the microprocessor. Also, it determines the functions performed by the 8251 because the microprocessor, it is sending the commands to the 8251 through this read and write control logic. The microprocessor it is going to write the control word into the control register, and according to the status of the control register, the modes and the functions of 8251 they will be decided. Okay, so basically we can say that the microprocessor it is controlling the functions of 8251 through the control register. Okay, and also this read and write control logic, it monitors the data flow, that the data is going to either flow from 8251 to microprocessor or from microprocessor to 8251, because it is having the two signals, read and write. So when the microprocessor is reading, it is the data flow is from the 8251 to the microprocessor. When the microprocessor is activating the write signal, means the data flow is from the microprocessor to the 8251. So it is monitoring the data flow also. So we can say that these are the three functions performed by this read and write control logic section. Now this section, it is having three registers. One is the control register. Second is the status register. And third is the data buffer. So control register, in which the control word is written, status register, from where the status of the 8251 can be read by the microprocessor, and data buffer, which is storing the 8-bit data. So these three registers are included in the read and write control logic. Now in the block diagram you have seen that along with this read and write control logic, we are having different interfacing signals also, like reset, clock, C oblique D, and read, write, and chip select. So let us study the function of these interfacing signals. First we are having the read and write signals. So read and write are used to perform the read and write operations with the three registers: control register, status register, and data bus buffer. So when read is activated, the data which is available in the data buffer that can be read by the microprocessor, or the status information can be read. If write is activated, then the command word or the control word will be written into the control register. So we can say that read and write are used for read write operations with the three registers. Okay. Next signal we are having is the C oblique D. Now this signal, its full form is C is for command and D is for data. So when this signal is active high, means when we are having the logic 1 over this signal, then command is activated, means whatever data is there, that is the command word. And if this is active low, means 0 is available on this line, then whatever data is there, that will be the 8-bit data. So it is used for selecting the when this command is activated, then control register is selected for writing the control word or reading the status word. When this command is selected, when data is selected, then data buffer is selected for read write operation. So you can see that both these signals, they are deciding that whether the data is going to read or written into the three registers. So operation will be selected by these two signals and registers will be selected through this signal. When command is activated, means control register and status register will be selected. When data is activated, then data buffer is selected. Next signal in the read write control logic is the reset signal. Now when this signal is high, the 8251 programmable communication interface, it enters into the idle mode. Idle mode means that all its operations will be stopped and it is going to come back to its initial conditions. And whatever command word is written into the microprocessor after this reset, that will be treated as the mode instruction of the 8251. So this reset signal, it basically resets the 251. It is going to reset all its conditions and bring it into the idle mode. It is not going to perform any operation, going to terminate all these operations and come into its initial conditions. The command words, they will be cleared out, status information will be cleared out, data bus buffer will be cleared out. Okay, so all values are bring to the 0 0 condition. Next signal is clock signal. So this clock signal, it is used to provide the clock input to the 8251 for communication with the microprocessor. So this provides clock input for 8251 to communicate with microprocessor. So wherever the 8251 is requiring any clock input, that will be provided through this clock signal. Next, we are having the CS bar, which is used to select the 8251 chip. As this is having a bar over it, so it's an active low signal. So active low means when the value is 0, then this signal will be activated. Means the microprocessor, when it wants to communicate or send the or receive the data from 8251, first of all it has to select the 8251 chip. If the chip is not selected, then no communication will be done. So first of all, microprocessor has to activate this chip select signal for performing any communication with the 8251 programmable communication interface. So this was the read and write control section. Next section is the transmitter section. In the transmitter section, whatever data the 8251 is transmitting, that is stored in the transmit buffer. This transmit buffer, it is going to convert the parallel data received from the microprocessor, convert it into the serial data, and then transmit it to the peripheral devices. So here it is written parallel to serial conversion. So this transmitter section, it is having two blocks, transmit buffer and transmit control. Transmit buffer, it is an 8-bit buffer which is storing the 8-bit data and performing the conversions from parallel to serial conversion. So this transmitter section, it is going to transmit the data to the peripheral devices. So microprocessor, it will send the data. It is going to send the parallel data to the 8251. So parallel data will be converted into serial data, and then the serial bit will be transmitted through this. Now the transmit control, it is checking the conditions that whether the 8251 it is ready for the transmission of data, whether this bit is transmitted to the device or not, at which rate it is transmitting. So all these functions are controlled by the transmit control block. So this transmitter section, what it does, it accepts parallel data from the microprocessor and convert it into serial data. Now this transmitter section, it consists of two buffers. Okay, one is it is double buffered. So it is having, one is the buffer register and second is the output register. So this transmitter section, it is double buffered. It is having two register. One is the buffer register which is storing this parallel data from the microprocessor, and other is the output register which is converting that parallel data into the serial data. Okay, so buffer register, function of buffer register is to holds the 8-bit parallel data and output register convert parallel data into the serial data, and then this serial data will be transmitted to the peripheral devices through the pin TXD. Okay, Now, when this output register is empty, buffer register is going to transfer the data which is there in the buffer register, that will be transferred into the output register. So in this way, the processor, it is loading again and again the 8-bit data into the output register. If we see the communication, microprocessor, that is MPU microprocessor, it is sending the data to the 8251, and here we are having the transmitter section. In this transmitter we are having first the buffer register, and second we are having the output register. So data from a microprocessor, it is first stored in the buffer register, then it is going to be transmitted to the output register, and output register will send it to the peripheral devices. Now when this output register is empty, again the data will be loaded into this through the buffer register, and that will be converted into serial form and again transmitted to the input output devices. Now in this we are having data is transmitted through this TXD pin. In the transmit control we are having three signals: TX ready, TX empty, and TXC. So what is the function of these signals? TX ready signal, it goes high when buffer register is empty. So when this buffer register is empty, it means that microprocessor, it can send more data to the 8251 so that it can be transmitted to the input output devices. So it is telling that the transmitter is ready, it can receive the data from the microprocessor. When TX empty is high, it means that the output register is empty, means the data which is there in the output register, that has been transmitted to the input output devices. Now next data can be loaded into it. So high when output register is empty. So TX ready, transmitter ready, it is telling us that the transmitter is ready to accept more data. TX empty means that the transmitter has transmitted the data to the peripheral devices. TXC, because it is the transmitter clock, so this is low, and this signal controls the rate at which the bits are transmitted. So this is the transmitter clock, so it will be equal to the clock frequency. Now there can be some factors by which, like 1, 16 and 64. These are the factors. Like when the factor is 1, it means that the transmitter clock is equal to the clock frequency. When the factor is 16, means the transmitter clock is 1 by 16th of the clock frequency. When we are having 64 as the factor, then transmitter clock will be 1 by 64 of the clock frequency. So here this TXC, it is deciding or it is deciding the rate at which the bits are transmitted by the 8251. So this was our transmitter section, which is transmitting the data from 8251 to the peripheral devices and converting the parallel data into the serial data. Next section is the receiver section. Now receiver section, it has to receive the data. So it is going to receive the serial data and convert it into parallel data and provided it to the microprocessor. So the function of receiver section is to receive serial data from the peripheral devices. Now, just like the transmitter section, the receiver section is also double buffered. Here we will have two registers. One is the input register and another is the buffer register. So input register, it is accepting the serial data and converting into the parallel data, and that parallel data will be held by the buffer register. So function of input register is to convert serial data into parallel data, and buffer register holds the parallel data. So input register, it is converting the serial data into parallel data. So first it is going to receive the bits from the peripheral devices. So whatever is the first bit, the 8251 will treat it as the start bit of the data. After that start bit, if it is whatever bits it is getting, it will consider it as the data, and then it is going to convert it into the parallel form and store it into the buffer register. So in the block diagram, you can see that receiver section, we have written here that RxD pin, it is receiving the data, and this receive buffer, it is converting it into the parallel form and providing it to the internal bus line so that it can be transmitted to the microprocessor. Now here also we are having two sections, receive buffer and receive control. So receive control, it is controlling the various operations of this receiver section. Here we will have different signals like Rx ready, Rx see, and sync detect and break detect. So let's study these signals. We are having Rx ready. This signal will go high when the input register, it is loading the data into the buffer register. It means that the 8251, it has received the data from the peripheral devices, it has converted into the parallel data, and now it is ready to accept more data from the peripheral devices. So it is telling the peripheral devices that it is ready to accept more data. So Rx ready means receiver is ready. It is high when input register loads a parallel data into the buffer register. Next line was RxC, which is the receiver clock. Just like the transmitter clock was controlling the rate at which the bits are transmitted, RxC, it is controlling the rate at which the bits are received by the 8251. Here also we will have different frequencies depending upon the factor 1, 16 and 64. So we can say controls the rate at which the bits are received by the 8251 or the USA RT. Next, we were having the sync detect and break detect. The function of this signal, it is dependent upon the mode, like whether the synchronous mode is selected or asynchronous mode is selected. So when synchronous mode is selected, then this signal will act as the SYNDET, that is sync detect. Because in synchronous mode, along with the 8-bit of data, the sync characters are also sent. So to detect these sync character, if any of the sync character is detected, this signal will go high. Now in the asynchronous mode, here it is acting as an input signal. But in asynchronous mode, this pin will act as an output signal. Okay, so you can see in the block diagram that this signal sync, detect, break, detect, it is having double arrows. So it can act as an input signal also and as an output signal also. Okay, so sync detect is selected, so it will act as an input signal, and output signal means it will act as BD or break detect. Because in asynchronous mode, along with the data, we are having the break characters, that is the start and the stop bits are there. So if these bits are detected, then this signal will go high. So that is the function of the sync detect and break detect signal. So this was the receiver and the transmitter section. Next we are left with the modem control section. This modem control section allows to interface a modem with the 8251, like over the telephone lines when we are connecting a modem for the internet. So that modem can be interfaced with the 8251 through this modem control section. So if the data is to be transmitted over the telephone lines, so modem will be used. So modem can be interfaced with the 8251 through this section. So what this section does, this unit provides the handshake signals for this modem interface. And what are these handshake signals? DSR, DTR, CTS, and RTS. All these are active low signals, so they will be active when their value is 0. DSR is data set ready. This is an input signal. DTR means data terminal ready. This is an output signal. So when the receiver means 8251 is ready to accept the data, then data set ready is activated. When data terminal ready means output, this is when the modem is ready for sending the data, and data terminal ready means 8251 is ready to accept the data. CTS, it is an input signal which is clear to send. And RTS is an output signal which is request to send. So this is a request which is sent by the 8251 to the modem that now you can send the data, and clear to send means that the modem is sending to the 8251 that you can send the data to the peripheral device. Okay. So these are the handshake signals which are used when a modem is interfaced with the 8251. So these are the 5 sections of the programmable communication interface 8251, which is also known as Universal Synchronous Asynchronous Receiver Transmitter, which is used by the microprocessor when it is interfacing or communicating with the peripheral devices. So to perform the parallel to serial and serial to parallel conversion, this 8251 communication interface is used. So I hope that this block diagram of 8251 is clear to you. Thank you.